In this video we're going to talk about gamma functions and their properties. One of the most common representations of gamma function is the following. Gamma of p equals integral from 0 to infinity of e raised to negative x times x to the power of p minus 1 dx. To be precise, this is only true for positive values of parameter. However, this formula is very useful anyway, and it is widely used for solving problems. Another way to introduce gamma function is the following. Gamma of p equals gamma of p plus 1 over p, which holds for arbitrary values of p, positive, negative, fractional, or even complex. Now let's return to that first integral and discuss it. First of all, notice the limits of integration. They are 0 and infinity. Infinity means that we're dealing with an improper integral. Another type of singularity appears when p parameter is less than 1. In that case, if x equals 0, an expression under the integral tends to infinity. Now what we have there under the integral is a product of two functions, exponential and a polynomial. And the whole integral is the area bounded by the product curve and the x-axis on the interval from 0 to infinity. Now let's pick a few positive integer values for p parameter and try and picture that area. Say p equals 2, and then we have gamma of 2 equal to the integral from 0 to infinity from e to negative x times x to the power of 2 minus 1, which is 1, so we have simply x dx. So we have an exponential function multiplied by the linear function. Let's graph them. So here goes the exponential function. And a straight line. Now we'll start multiplying values of these two functions for each x moving from 0 towards infinity, and thus obtain a product curve. And the area bounded by this curve and the x-axis is the one we need to find. As you can see from the graph, the product curve has intervals of increase and decrease, and therefore a maximum. Let's find its x-coordinate. And for that we need to take an expression under the integral, find its first derivative, and equate it to 0. So we have negative e taken to the power of negative x times x to the power of p minus 1 prime equals negative e to the negative x times x to the p minus 1 plus p minus 1 times e to the negative x times x to the p minus 2. We can factor out e to negative x times x to the p minus 1 and obtain e to the negative x times x to the p minus 1 times negative 1 plus p minus 1 times 1 over x equals 0. Now exponential function never turns to 0, and assuming that x is equal to 0 as well, we can divide both left and the right sides of this equation by e to the negative x times x to the p minus 1 and obtain the following equation. P minus 1 times 1 over x equals 1, and x equals p minus 1. And that is the x-coordinate of the maximum of a product curve. equals b minus 1. So for the case we have been considering, x-coordinate of a maximum is b minus 1, but b equals 2, and that means that x max here equals 2 minus 1, which is 1. And that is what we have. Now let's pick another value for b. Say b equals 3. And so we'll have gamma of 3, which is equal to the integral from 0 to infinity of e to the negative x times x to the power of b minus 1, which is 3 minus 1, which is 2, dx. This time we'll have an exponential function multiplied by a quadratic function. Let's graph them. So here comes the exponential function. And a quadratic function. Parabola. And again, we'll start multiplying values of these two functions for each x, moving from 0 towards infinity, and obtain a new product curve, which will have a maximum as a coordinate b minus 1, which is 3 minus 1, which is 2. As we can see from these two graphs, as the order of a polynomial function increases, the product curve goes higher and the bounded area therefore is increased as well. So increasing of b parameter leads to increasing of gamma function. Gamma function is of great importance. It is widely applied in mathematics, particularly in probability theory, and many other fields. What's really important is that gamma function is closely related to the notion of factorial. For integer and positive arguments, gamma function is the following. Gamma of n equals integral from 0 to infinity of e to the power of negative x times x to the power of n minus 1 dx, where n is a positive integer. Let's consider gamma of n plus 1. It is equal to the integral from 0 to infinity of e to the negative x times x to the n plus 1 minus 1 dx, which is equal to integral from 0 to infinity of e to negative x times x to the n dx. And let's evaluate this integral using the rule of integration by parts. So we'll have u equals x to the n, du equals n times x to the n minus 1 dx, dv equals e to the negative x dx, d equals negative e to the negative x. So we have negative e to negative x times x to the n from 0 to infinity minus integral from 0 to infinity of negative e to negative x times n times x to the n minus 1 dx. If we substitute 0 and infinity into this expression, we'll have 0 minus 0, and therefore this first element gives us 0, and leaves us with a second integral. We can factor out negative n and obtain the following. N times integral from 0 to infinity of e to the negative x times x to the n minus 1 dx, which is nothing but the initial gamma function, gamma of n. So we've obtained that gamma of n plus 1 equals n times gamma of n. So once again, we've showed that gamma of n plus 1 equals n times gamma of n, which is a recurrent formula. So if we apply it consequently, we'll obtain the following. Gamma of n equals n minus 1 times gamma of n minus 1. And we can substitute this expression into the previous formula instead of gamma of n, and we'll have n times n minus 1 times gamma of n minus 1. And then gamma of n minus 1 equals n minus 2 times gamma of n minus 2. And again, we can substitute this expression into the first formula instead of gamma of n minus 1 and obtain n times n minus 1 times n minus 2 times gamma of n minus 2. And we'll go on doing that until we'll have gamma of 2 equals 1 times gamma of 1. And then gamma of 1 can be evaluated. It is equal to integral from 0 to infinity of e to the power of negative x times x to the power of n minus 1, but n equals 1, so we have 1 minus 1 in the power next to x dx, which equals integral from 0 to infinity of e to the negative x dx, which equals negative e to the negative x from 0 to infinity, which is equal to 0 minus negative 1, which is 1. So what we'll have here is n times n minus 1 times n minus 2 and so on times 2 and times 1. And this sequence is nothing but n factorial. So we've shown that gamma of n plus 1 equals n factorial. Up to now, we have only considered positive integer values for the parameter of gamma function. But what if we try to say negative? That is where the formula gamma of p equals gamma of p plus 1 over p comes in handy. Because as we've mentioned at the very beginning, this formula holds for any value of p, including negative and even complex. So it turns out that gamma function generalizes the notion of factorial on fractional, negative, and even complex numbers. Now let us consider a couple of other properties of gamma function. There is a so-called Euler's reflection formula, and it goes like this. Gamma of p times gamma of 1 minus p equals pi over sine of pi times p, which holds for the values of the argument lying within the interval from 0 to 1. Then there is a so-called duplication formula, which goes like this. 2 to the power of p minus 1 times gamma of p over 2 times gamma of p plus 1 over 2 equals square root of pi times gamma of p. If we substitute p equals 1 into this formula, we'll obtain the following. 2 to the power of 1 minus 1 times gamma of 1 second times gamma of 1 plus 1 over 2 equals square root of pi times gamma of 1. Now let's see. We have 1 minus 1, which is 0, and 2 raised to the power of 0 equals 1. Then we have gamma of 1 plus 1, which is 2, over 2, which is 1. And we have already considered that gamma of 1 equals 1. And same here. And so this way we've obtained the following equality. Gamma of 1 second equals square root of pi. Also, there is an interconnection between beta and gamma functions. And it goes like this. Beta of p and q equals gamma of p times gamma of q over gamma of p plus q. So beta function can be expressed as a combination of gamma functions. Now let's try and understand why is it so. Let us recall what we had for beta function of positive integer arguments. Beta of m and n, where m and n are positive integers, equals m minus 1 factorial times n minus 1 factorial over m plus n minus 1 factorial. We also know that gamma of n plus 1 equals n factorial, which is the same as if we'd written gamma of n equals n minus 1 factorial. This first formula is just more commonly used. So taking that into consideration, we have that beta of m and n equals gamma of m times gamma of n over gamma of m plus n. Here we have the graph of gamma function of a real argument. If we look on its right, we'll notice that for positive values of the argument, gamma function is continuous. But for p equals 0 or p is less than 0, gamma function has singularity points. Let's see why. We remember that gamma of p equals gamma of p plus 1 over p. If we substitute p equal to 0 into that formula, we'll have gamma of 0 equals gamma of 0 plus 1 over 0, which is gamma of 1 over 0, which is 1 over 0, which equals infinity. We could also take positive 0 as an argument, which actually is not a 0, but a really small positive value, and have 1 over positive 0, which equals positive infinity. Or else we could take gamma of negative 0 and obtain 1 over negative 0, which equals negative infinity. And that is exactly what we have on the graph. If p parameter is approaching 0 from the right, gamma function tends to positive infinity. And if p parameter is approaching 0 from the left, gamma function tends to negative infinity. Now let's consider gamma function at an argument which is a negative integer. So we'll have gamma of negative k, where negative k is a negative integer, equals gamma of negative k plus 1 over negative k. And we can apply this formula to the numerator and obtain 1 over negative k times gamma of negative k plus 2 over negative k plus 1. And we can apply it again and have 1 over negative k times 1 over negative k plus 1 times gamma of negative k plus 3 over negative k plus 2. And we can go on doing that until we've reached gamma of 0, and this whole expression can actually be reduced to negative 1 to the k times gamma of 0 over k factorial. But we've already shown that gamma of 0 equals infinity, and therefore for each negative integer argument of gamma function, we'll obtain positive or negative infinity. And those are, and there are no other singularity points of gamma function other than these. And that's how things with gamma functions go. Enjoy.